Hello, how are you doing? This is Mike here again, and in this video we're going to talk about polar coordinates, but specifically how they lack uniqueness, how they are not unique. So polar coordinates are not unique. So very different than working in a rectangular plane. In a rectangular plane, you could say that all those points are unique, but in polar points are not unique. So let's go ahead and look at some examples. But before we do that, if you're following from my video prior, I know sometimes people get confused in terms of polar points, polar coordinates, or polar points, and the ray that creates the polar point. So first of all, let's just go ahead and look at the point 1 comma 7 pi over 4, 1 comma 7 pi over 4. So this right here, this first circle is going to be my value of 1. So everything here that I'm dotting is going to be my value of 1. I just want to be very careful. I don't want people to think that's the actual point. But this is going to be my radius of 1. This is 2. This is 3. This is 4. This is 5. This is 6, and so forth. And this extends on out to infinity. And if we look at 7 pi over 4, 7 pi over 4 is almost 8 pi's over 4. And this is a value of 2 pi. But I really am going to be going 7 pi over 4. I'm really going to go over 7 pi over 4, which is a value of 8 pi over 4 minus pi over 4. So I'm sitting right down here at this negative pi over 4, this negative pi over 4 value. So right down here, we are sitting at this negative pi over 4 value, if that makes any sense. So this right here is going to be 315 degrees, which is negative pi over 4, and this is also known as 7 pi's over 4. So there's a lot of different ways we could name this angle. So if I travel out here, and this is my point. Actually, let's change this from 1. Let's change this to something a little bit larger. Let's change this to 4. This is something a little bit easier to visualize. So this point here, this point here is going to be 4 comma 7 pi's over 4. If I attach from the pole to this point the ray, this is my value of r equals to 4. So the point is the red dot. The point is the red dot. The ray is the length from the pole to the point. So I know sometimes people are really, so I've seen some lectures and I've seen people discuss polar points, and just I think for point placement, they usually draw the ray. They draw the ray just to make the point a little bit easier. However, if you are plotting the polar coordinate 4 comma 7 pi over 4, it is just the red dot. If you add this value of the ray, I know sometimes it can help place the point because you might travel 1, 2, 3, 4 values of the radii, four circle lengths. I hope I'm saying that right. Just be very careful that we do have the point 4 comma 7 pi over 4. But as I said before, as we titled this video, this point is not unique. So maybe you might be able to think of another way we could write out this point. Some of you may recognize that we always are going to have this relationship between the length from the pole, the origin, to the coordinate point, and you could also travel a negative angle direction. So we could travel 4 comma negative pi over 4. So we could travel 4 negative pi over 4, which means from the polar axis, and again, this is the polar axis, we're traveling a value of negative pi over 4. Negative pi over 4, which means that we're going clockwise versus counterclockwise. So that's another example of how we might be able to look at this. Or we could say this is going to be a value. We could call this a value again of 4. And let's say, for example, we look at 2 revolutions. So we look at 15 pi's over 4. 15 pi's over 4. So maybe some of you recognize that I don't want to just travel around this once. So I'm traveling around this pi over 4, keeps going, keeps going, keeps going. Then we are at right here. So 1 revolution is 2 pi's, also known as 8 pi over 4. 8 pi over 4, but we still have to go another 7 pi's over 4. So then we travel around another revolution until we get to 15 pi's over 4. So this has an infinite amount of ways, there's an infinite amount of ways to name one point. So just be very cognizant about that we could see these points named in several different ways. So you want to definitely practice using both positive and negative angles based off of that polar axis. So there is a general formula. There is a general formula that we can use. So let's go ahead and write that out. So let's go ahead and say a general formula for points that are consistent for a polar point P. And if it has the coordinate r comma theta, I feel like I'm writing a 3-year-old, then r comma theta plus 2 pi, and we'll call this 2 pi times n, and r comma theta minus 2 pi times n will also be the same point. But I have to just describe here, so I'll say that maybe where n is a positive integer, because this could just be, 1 revolution, so n would be a value of 1, or negative 1 revolution, it could be a value of 2, 3, 4, and so forth. So we also recognize that these will also be points that exist at r comma theta. So if r comma theta is a point, if we add 2 pi times n revolutions, or we subtract 2 pi times n revolutions, we're going to have the exact same point. So we recognize that the value of theta can change, but yet still give us the exact same point. Some may beg the question, what about r? So let's examine, can r, the value of the radial coordinate, so we'll call the radial coordinate, can r change and still arrive at the same point r comma theta? And the answer is yes. So let's go ahead and just look at this. So I'm just going to draw here, and then let us draw here. So we'll call this guy the polar axis. That guy's going to be the polar axis. And let's say that we traverse an angle of 5 pi's over 4. So we're going to traverse an angle of 5 pi's over 4. We will call this value, I'll see if I can write slanted, the terminal side. That value is considered the terminal side. So just be very cognizant that if we were to extend this dotted line would be known as the extension of the terminal side. So again, a lot more nomenclature, just be very cognizant about it. So let's say that we want to look at the point 3 comma 5 pi's over 4. 3 comma 5 pi's over 4. So I'm going to take this and I'm just going to, I wonder if I can just, there we go. I guess I'll just draw it again. Okay, so I'm just trying to be as articulate as possible. Okay, awesome. So I'll copy this for future purposes. So let's say that I want to graph the polar coordinate 3 comma 5 pi's over 4. We recognize that I'm going to travel this distance, and that distance is the angle 5 pi over 4, and then I want to travel out a value of 3 units from the pole. So this is going to be the point 3 comma 5 pi's over 4. But as we said before, there could be a way for us to change the value of the radius such that I still arrive at that exact same point. And that's going to be using a value of a negative radius. So if we were to examine and then determine the extension of the terminal side, we realized that we could get to the extension by subtracting, and notice this here is a value of pi. This value is a value of pi. So pi can be written lots of different ways. Pi can also be written as 4 pi's over 4. So if I want to find the extension of the terminal side, I take 5 pi over 4 and I subtract 4 pi's over 4, and I recognize that this extension is just going to be a value of pi over 4. Pi over 4. But I don't want the value of the radius along the extension of the terminal side. I still want the value of the radius along the terminal side. So instead of traveling in a positive direction, we're going to travel in a negative direction. So we could also write this point as negative 3 comma pi over 4. Because if I look at this value as being pi over 4, this now becomes my terminal side. So normally I would travel out 1, 2, 3 values. However, my radius is negative 3, which means I'm going to travel towards the extension of the terminal side. So now I'm going to have negative 1, negative 2, and negative 3, and notice we're at the exact same point. So this is going to be negative 3 comma pi over 4. So 3 comma 5 pi over 4 and negative 3 comma pi over 4 are the exact same values. If you have a negative radius, you will travel towards the extension of the terminal side. If you have a value that is positive, a radius that is positive, you will travel along the terminal side of the angle. So just be very cognizant that you might be able to see lots of different ways to write the same polar coordinates. So let's just come up with a general rule. Let's just come up with a general rule. So a general rule of these points. So the terminal side of an angle theta plus pi is the extension of the terminal side of theta. So just to explain what this means, again, I always like to explain. So if I travel from here to here, and this is a value of theta, this will be my terminal side. But if I travel another value of another value of pi, so my total angle will be theta plus pi, this will now be the extension of the terminal side of theta. So we can then write a rule. We can define negative radial coordinates by agreeing that negative r comma theta and r comma theta plus pi are polar coordinates of the same point. So we can change the value of r by altering the magnitude, by changing the magnitude. Well, I guess you could say by negating the magnitude, so not by changing the magnitude. Magnitude is always positive, but by negating the magnitude, no, by just, all we have to do is, I'm sorry, not by negating the magnitude, just by negating the radius. So nothing about magnitude, just please excuse that I said that. So if we want to negate the value of the radius of that radial coordinate, then we have to add a value of pi to that angle describing it. And that way we can arrive at the same angle. Very similarly to if we add a value of 2 pi just to the angle, we keep the value of radius. So there's a couple different ways that we can rewrite every single polar coordinate.